Okay, so everybody, if I could have their attention. So, we are coding Dojo, Society and University of Manchester.
Oh my god,
I guess I can use
I
the
love that
back
guy. He's for me.
I guess you can kind of hear it, whatever. So, my name is John, and we're here to talk, this is Anka and Andre, wave at the crowd, and we're here to talk a bit about pathfinding and real-world applications. So, I'm just going to go over a short overview of what we're going to cover. So we're going to have, first of all, I'm just going to talk to you about why would you want to know anything about pathfinding, like where do you use it. We have, and a few methods of how to do pathfinding. Very obvious one, depth first search, breadth first search, double star breadth first search, die strat, A star, and a bit of questions and answers at the end. So, pathfinding, you find it everywhere in your life. So you kind of do it every day, right? So you have this map in your head of Manchester, and you need to go to uni. How do you actually know how to get from your home to uni and still be on time for lectures, or at least halfway through them? Like a few examples over here you can see include StarCraft. If you
Not make sure the protocol.
It's a bit old, I know, but I mean I love the game. How do the units know where to go if you click somewhere really far away? How do they do the mapping? You've got GPS, an obvious one. I mean, it kind of goes together with the example I just gave before. And you've got the internet. I mean, when you have packages going throughout routers, how do they know which path to take, which one is the best one, unclogged and so on? So.
Okay, so now I'm going to present you the most obvious one of them, the depth first search. How does this work? Well, it's like when you enter a maze, and you just go straight in the first direction you see until you bump your head up the wall. And then you go back and try again. So the algorithm itself just marks a node, the starting node that visited, and as it goes, it discovers new paths and marks each node it goes where it visited. Now it goes through D, and from here on, there's nowhere else it can go. So it just goes back and tries a new path. It marks every node on the way as visited. Basically, it's the easiest algorithm, as it won't find necessarily the shortest path between two nodes, but it will find a path between one node and another. This is a pseudocode, and as I said, you label V the starting node as visited, and you go to each vertex that is adjacent to your current node, and then do a DFS from there on. Now, something a little bit more appropriate for the shortest path. This is a breadth first search. Here, you don't go in the maze straight on. Yeah, but first I'm going to show you a bit on the code. So here you take each adjacent node, your current node, and add them to your queue. And then you go through all the different directions simultaneously. So you're going to make a circle around the starting node until you find the end node. To exemplify that, I'm going to use this one. Okay, so here we have a maze. The green point is the starting point, and the red point is the end point. If we're going to do a breadth first search from the starting point, you're going to see exactly how it works. It goes on every adjacent vertex, all this. Now, this is more okay. Now, more optimized way to do a BFS in a maze or in a graph is to start from both the start point and the end point at the same time. This way, what I'm saying there, when you're using a single BFS, the distance, this area of what you're searching is pi r squared. When you're using double star BFS, you have two circles starting from both points at the same time, each being pi r over 2 squared. Added together, that would be half as much as doing one single BFS. We'll use breadth first search.
I hate when you say it so much.
As you can see, it starts from both points, and it does two circles, which is they're going to meet in the middle. The execution time is a lot smaller.
I haven't.
Yeah, okay. Now, I'm going to show some interesting application of breadth first search. The first one is from Facebook. I think you all know how Facebook organizes data. The users are nodes, and the friendship between users are edges. What would happen if you would traverse this graph, the Facebook graph, with a BFS? Well, it's going to get you to a result, and you're going to observe that between any two people in the world, there is a connection by at most 5 nodes in between. This is called the small world experiment. It was first done in the 1960s, I believe, but a lot before Facebook. And it was at that point, it was shown that it was at most 6 nodes. It's called the sixth dimension, six separation, something like that. You can search the Google for the small world experiment. Now with Facebook, they show that between any two people there are at most 5 nodes, and in one country even at most 4 nodes. Another application are web crawlers. So what is a web crawler? Web crawler is an internet bot that systematically browses the web. It goes from page to page, and it's mostly used for indexing. The most well-known crawler is called the Google bot. Google uses this method for its search optimization. It goes from URL to URL and indexes each page so that when you search something on Google, it will be a lot faster to find you what you're looking for. And now,
yeah, I won't try to bore you. Who knows how to read that? Yeah, that's Dijkstra. Have you heard about it? Not you. Yeah? How many of you have heard about it? Oh, okay. Well, people to see. You know this guy?
No.
Yeah, exactly. So this is Edgar Dijkstra. He's a very, very smart guy. And what he designed, so the contribution he made, probably the most important, is the Dijkstra algorithm. Now, imagine that in the both previous algorithms, the DFS and the DFS, you went from one node in the graph to the other node in the graph with no code, yeah? So, 0 code. But now imagine, for example, that you are in a city, okay, you have a country, and you have like, I don't know, 20 cities, yeah? And each of them, the distance from city A to city B is, I don't know, X kilometers, X miles, yeah? The point of this algorithm is that it's finding the shortest path between nodes in a weighted graph. So the difference is the cost to get one node to another is not 0 in each case. It can be different. And it's widely used in network routing protocols. For example, the intermediate system to intermediate system protocol, or ISIS, no pun intended, or the open shortest path first. And as for today, this is the fastest known shortest path algorithm if implemented quite efficiently. In the case of arbitrary directed graphs with non-negative weights. Now, how it works, I won't show you pseudocode because this is quite long and it won't fit on a slide. But let's suppose you have that graph, yeah? So you have 4 nodes, A, B, C, D, and you see the weights to traverse the graph. For example, the cost of getting from A to C is 3, from A to B is 7, and so on and so forth. The starting point is 8. What you want to do is that start. So at the beginning, you're starting with A, and you're questioning yourself. Well, what's the? That's it. Oh yeah. So, what's the shortest distance from A to any other node? Well, so from A to A, it's 0. Obviously, because you don't have to do anything. From A to B, 7. Yeah. These letters here, yeah, I've just written these letters to know which vertex I came from. From A to C is 3, and from A to D is 2. What I will do next is I have completed, so I'm no longer taking into consideration point A. I'm only at the next step of the algorithm. I'm only taking into consideration points B, C, and D. And what I do is actually take the vertex which has the minimum cost. Yeah. So in this case, it's D. And I will ask myself, yeah, what's the shortest distance to get from D to any other points that I'm now considering? So I'm not considering A anymore. So what's the shortest distance to get from D to B or C? Well, if I'm going from D to B, it's 4, yeah, plus the 2 from A, this will give me 6, which is quite smaller than this. If I go from D to C, that's also 5, plus 2, it's 7. I don't want to pick that, yeah? So this will stay the same. Now, I've finished considering A, I've finished considering D, now I'm considering C and B, and again, I will go with the lowest one, which is C. And I only want to see if I can get to all the other unvisited nodes, in this case, B is the only one left, with the lower cost. Well, from C to B with cost 1, and it gets me 3 to arrive at C. So 3 plus 1 is 4, which is better than 6. And yeah, I'm done. Now, if I want to check how I got there, if I want to see the path, it's easy. So, for example, if I want to start at A and go to, I don't know, B, obviously, I'll look at this. Yeah, so the minimum cost is 4, but I came from C, and C came from A. So actually, this is the shortest path. Hopefully, this was clear enough. But what I wanted to show you is what do you expect that would happen in case that I would run a dice star algorithm, but with all the weights equal to 0. So basically, I'll go to, if all of these are 0, I'll go to A, yeah, 0, 0, 0, 0. I'll pick the next one, 0, 0, 0, 0. So it will visit each node. It will behave exactly the same as the DFS. And let's do a quick demonstration. Let's pick the maze. So again, let's restart the BFS. This is how the BFS behaves. And if we're doing dice draw, it behaves exactly the same. It's a shame that I can't show you how it behaves when we actually have weights, but yeah. Now I'll let my colleague John talk about the other one.
Let me start. Okay. So if you guys kind of got what Dash was all about, right? So you've got your list of visited nodes, unvisited nodes, you go through them, which one is closest, I'm going to go to that one, and so on. But let's consider this scenario, right? So right now you're in the middle of the road, okay? And it's really foggy, you can only see like a few meters ahead of you. But you can see your destination, which is this massive mountain peak. Oh, okay, so you're wondering, actually combine two pictures into one? I mean, I know you can't really see it here, but I mean, just want to talk about it. Now, when you're considering your path, how do you get to the mountain? Will you actually think about turning around and checking there? Or will you immediately just, okay, I'm just going to try walking towards the mountain. I'm going to go in that direction first. That's exactly what A-star does. It's basically Daisha with making the logical assumption that if I go towards my target, then I'm probably going to get there faster. So, what is the heuristic? I already kind of said it. So it's a logical assumption, a mental shortcut, an educated guess. Now I'm kind of going to go for the pseudocode. I know it looks fairly intimidating, but I'm going to make it fairly, I'm going to try simplifying it. So I only want you to pay attention to small bits of it, right? So you've got the closed set and open set. This is just like in Daisha. You've got nodes which you have visited and nodes that you are about to visit, right? But the difference between Daisha and A-star is that instead of leaving the graph with only the distance from the start to the node we got into, we're also going to add our heuristic and add the final distance. So I'm going to call G-score the distance where from my start point to the node I'm in, and F-score the final score, which is the distance from the start point to node I am plus the heuristic, which I assume would be. Right? So the idea of it, how does it go? It goes exactly like in a Daisha, right? But instead of getting the neighbor which is closest to you and going to that one, you're actually going to go to the neighbor which you assume in the end will be the closest to the endpoint. So what does that mean? That basically means that if so let's say we got to a node, right, whichever has the lowest final score, and then for each neighbor of this node, we're gonna tentatively try to see, okay, if we go through this node till the end, how much would that, according to our heuristic, take us to get to the end, right? Well, it take us the time it got us to get here, plus the distance between current and our neighbor. By distance, this is my heuristic. I just take the Euclidean distance, and if you guys don't know what that is, if you've got a grill, I'm going to talk about it later, but you know, it's just a simple mathematical formula between them. Okay? And then I try seeing, okay, is my tentative score smaller than the score I already got when I arrived to that neighbor later? If it is, then I care about this one, as in it's good enough and then I could continue with it. If it's not, then I already arrived to it before with a lower score, so I'm not going to add it to my list. Okay, so that's the way A-star works, and let's do a small demonstration of how it actually looks. So this is what I'm just going to show it to you in a very, you can see how, so you can see how breadth first search or Daisha work, but here's how A-star works. As you can see, it's a perfect straight line. And why is that? At every point, it thinks. So, which point is closer to my end point, and can I get to it? Since this neighbor is the closest I can get to my end point, we're just going to continue that way. I'm just going to show you the wall as well. So if I just build this wall here and do it again, it's going to drag it around until it can avoid the wall. Okay. And now, so the interesting part about A-star, the thing that makes it more used in common life than Daisha, is that you can control its behavior using the heuristic, and you can control it according to what problem you have, right? So, if your heuristic is 0, as in you just say, every node is the same for me. I don't know how long it's going to take till it gets to the end. I'm just going to put it 0. In that case, you just have an old Daisha. It does exactly the same thing as it would do. Now, if your heuristic underestimates the actual cost of getting to the goal, so you always underestimate it, then A-star will always guarantee that you will get an optimum path. Okay? The problem arises though, when you overestimate your heuristic, then it is guaranteed that it will find a path, but it's not guaranteed for it to be the best. Could anybody figure out why? Okay, so think about it this way. If I always overestimate my, so the easiest way, just think about it, if I've got a heuristic which grossly overestimates the cost from going from the cost to actually be to get to my endpoint, what happens is that it devolves into greedy best first search, which means it's going to continuously try going as close as possible. So it's kind of going to devolve into a bit of a depth first search, as in it's going to continue going down one pathway until it can reach its goal, and it only turns back if it's stopped somewhere. So I'm just going to actually show you that. So this is how my A star looks like, and this is how my best first search star looks like. In this case, exactly the same. Gonna have to be okay, as you can see, this one goes above. Yes. Okay. So, basically the reason why this one actually went down instead of going upwards was because when it arrived to these nodes, right, its idea of this, so its idea of going forward is that these nodes continuing this path would be exactly the same as continuing this path, because the heuristic draws overestimation. And what happened? It did continue this path, and it continued until it reached the endpoint. So it didn't even try exploring the other path, which could have been better. Yeah. So now you might ask me, so how do we actually get a heuristic? How do we implement, well, not necessarily implement it as much as think about it? Well, unfortunately, the answer is depends on the situation quite a bit. So you can think a very easy example is when you have a grid, right? So you've got the grid with blocks, how to actually do a heuristic. You know, you've got the very simple ways. You can either use the Manhattan distance, which is just this, basically get the absolute value between the difference between the end goal dot x, the start node dot x minus the end goal dot x and y. You know, get that multiplied by d, which is a constant. Another easy way is doing diagonal distance, which is very similar, and so onwards, right? Now, this is a good way of doing it for grid maps and whatnot, but you can think of it as being slightly wasteful in many ways, because this heuristic will obviously underestimate it by will underestimate the actual value by quite a bit. But what happens is, if we can get a heuristic which gets the end value exactly, so exactly the one we want, then A star would actually go the perfect path from the first go. So it would be perfect implementation. So what we'd love to do with our heuristic is get it as close as possible to the actual value, the real one till the end, but not go over it. In that case, we can't guarantee the result is optimal. But let's think of it in another way, right? So we can't, it's really hard to make this thing better. Let's say this is our grid, right? We've got walls and we've got all these points. It's kind of hard to think of a heuristic for this. I mean, you can obviously use the Euclidean distance, for instance, just draw a line from each point. But it's not that efficient now, is it? But we can do it another way. We can just change the map itself. So if you take this map, you can easily simplify it to only what matters, as in this. So if you look right, I'm just going to put them parallel, right? So we're only going to look at the waypoints in which we have gates, and then the shortest path to get to those things, assuming that we can go diagonally. But of course, I mean, we don't need to go diagonally. We can use the grid system as well. So these are the kinds of optimization which you'll see more often in the real world. Because making a good heuristic depends a lot on how you represent your data. Yeah? So then, now I'm just going to tell you a few reasons why you wouldn't actually want a perfect heuristic, or you wouldn't actually want your A star to calculate the shortest path. So let's say I'm playing my strategy game, okay? And I'm controlling my stormtroopers from this position, and I want them to come here and attack this Zerg colony. That's it. Now, when I right-click here, I obviously assume them, to just go the straight path and attack from that way. But what might happen if we have, especially terrain difference, let's say this is a really hilly area, in which case the cost of moving through here would be fairly high. And actually, if it goes around this way, it would be slightly faster. But that's a lot of the time counterintuitive. So this is kind of part of the whole idea. Make your heuristic for the problem you're facing. You don't necessarily want the best solution all the time. You want the one that you actually need. And that's the case for everything, in GPS as well, in network packages. You can't know, a lot of times you don't even know what the best path is, right? So you just do the one which seems more convenient in a way. Yeah. So that was our presentation on pathfinding. Did you guys get how dice from a star work? Just want to see if your hands have got it. Okay, a few people. Would you like for me to do an example and just walk over a star on a simple graph on paper? Yeah, cool. I'm going to go back and do this torture. Oh, Chris, let's move it. Okay. Can you see? Let's leave. Let's see. That's about how. Okay. So let's say we've got a simple graph, or no, let's say we've got a country, right, which has cities in these places, and these cities are also on an axis, right? So each of these cities have certain coordinates, and we've got certain rows between them. Okay. Since these roads, some of them are, better funded, better repaired, they're just nicer in general, or have less traffic on them. You have a certain distance for each of them. So you've got distance 5 here, 3, 1, 2, let's see, 2 again, and another 1. Okay, and we're trying to calculate the distance from this point till this point, which are also going to be 1, 2, 3, 4, 5. Okay, and now how would we do that with a star, let's say? So, since we know that each of these points has a certain coordinate, I'm not really going to stay and write them all just because it would take too much time, but since we know they have a coordinate, what we can calculate is the Euclidean distance between each of them, right? So we can say all of them will have a value h of node, which will determine the heuristic distance from them, from n till 5, which is our nth node.
Hear that?
Yeah? So, let's say for this node, our heuristic says something like, how much would that be? Let's say it's 5. This one is closer, so I'm going to put it to 3.5. This one is like 3. This one is even closer, so 2. And this one is obviously 0, right? So, right now we're going to have our visited and to visit lists. Okay? In our visited list, what we're going to put in the beginning, we're just going to put node 1, which is our start node. We're just going to put in the to visit list for now. Okay? And then we go for it. So we take the first item from the to visit list, which has the lowest overall score, which is 0, the score together, plus 5, which is 5. Right? You put it here, you cut it from here. Right. And what do? You go through each neighbor of 1, aka 2 and 3, and you add them to the list to visit, ordered by their final score. So the final score of 2 at this moment would be 5 plus 3.5, which is 8.5. And of 3, it will be 3 plus 3, which is 6. Yep. So we add them, we obviously add 3 in the beginning because it's closer, and then 2. And now we've visited 1. And now we're visited 1, so you can literally count it out of the whole thing. Then we get the next node to visit, so we get 3. We go to 3, and what do we say? Okay, so my cost to get to 3 is 3. Let's add its neighbors that again. But I've already added 2, so what am I going to do with this? This is where it comes to show that we're going to do the distance it takes us to get to 3, which is the distance it takes us to get. The distance it takes us to get to 2, which is the distance it gets us to get to 3, plus the distance between the 2 nodes. So it's 3 plus 1, 4, plus its heuristic 3.5, which is 7.5. Is this better? Yes, it is. So we automatically knock this one out, and we update its value in our toVisit, which normally would be a priority queue, which would allow for this kind of operation. And its new heuristic final value would be 7.5. And it would still be, it's already in the list, we don't need to update it. And we also add 4. 4 would be 3 plus 2, 5. 5 plus this heuristic is 7. 7 is actually smaller than 7.5, so we'll visit 4 before we visit 2. Okay? And we're finished with 3. Now we go to 4. So we go from 4, it took us to get here. It took us 5, 5 plus 1 equals 6. This is the score for the final node. And here is where we'd stop because we've already arrived at our final node, and because our heuristic determines that we're definitely going to, since our heuristic is smaller or equal than our actual value, this is guaranteed to be the best solution. And if you look at the graph, that is the case. I mean, you can actually find exactly the same path if you go 3, 1, 2 here. It would be exactly the same distance, but it doesn't matter for our example. So this is how we calculate the distance between 1 and 5. And if you want to reconstruct the path, that's fairly easy. You just have another variable which you say, okay, where did I come from for each node? So for 5, I came here from 4. From 4, I came from 3. And from 3, I came from 1. Okay. Yeah. So that's kind of an overview how it works. I can still see some confused faces, and that's normal. I mean, it's not necessarily the simplest algorithm. If you just keep in mind the idea of check the node which is closest to you and which you assume is going to be the fastest towards the end, that's A star. Check the node which is closest to you, that's Dijkstra. Check your neighbors first, and then their children, that's breadth first search. Check your neighbor, their children, so onwards till you can't go anymore, that's depth first search. And that is basically how it all works. Okay, so thank you for your attention. If you've got any questions and answers, now would be the time.
What if you don't have grid for each side?
So if you don't have a grid, that's an interesting thing. So if, for instance, this, instead of it being a nice city landscape like a country, which has a simple grid thing, it was routers with networks, then that's when it becomes tricky. So unfortunately, there is no, commonly used algorithm if you don't have some kind of knowledge about the space you're in. But you can think of stuff like, if you, what happens a lot on the internet, for instance, is that when you've got the series of routers, they pre-compute the values, the distances between them. And when they pre-compute these distances, they just give A star that perfect heuristic. And that's kind of the best case you can go about it. But when you can't really do that kind of stuff, you still kind of do, I'll be honest, it just depends from case to case. I wish I could answer it in a very generic, this is the answer form, but unfortunately there is no answer. Yeah.
When you did one of the A-star grids, it was the open field ones, but it didn't take the shortest path. It went downward, then it went right, rather than just straight toward the other one.
Which, are you talking the slides or I just went out?
One of the grids.
The overestimate one.
Oh, one of the grids. These ones? Yeah.
Heuristics Manhattan, so it would produce the shortest distances the crow flies if you use it, assuming that.
Yeah. So yeah, that's the thing. Even though this thing actually shows the path as in it can go in diagonal, it can only work in grids. So that's the reason why it may have been different there. I mean, as far as I'm aware, it's not working. Unless everything you've been working on the internet is all lie. Probably not. Okay. Thanks for questions. Any other questions?
So if the second pass to go on, would you first try to make the pass clear and then go back and go on?
Okay, I think I kind of got your idea. So the way A-star would kind of try to do this, especially with the Manhattan distance, is that it would initially try to go down, like in this would be its perfect pattern, if you could just go this way. So what it does, it kind of goes this way, and then it chucks down first until the cost kind of becomes bigger than if it goes up. I can actually just show it to you in real life now. So just use Manhattan. Yeah, so as you can see, it first goes down in the thing. Actually, pause this yet. So it first goes down all around it, and then it tries the thing where it goes up, and then the other guy's going to go down this way, not going to work, and actually going to hit it from both. Yeah. Oh, and actually something I haven't really mentioned. For all of these algorithms, you also have the bidirectional thing. So it's basically the same idea, but instead of starting from just the start point, you start from both points. And what that usually does, I mean, we've explained mathematically why it's always better for breadth first search. But unfortunately for A-star, it's not always better to do this. I mean, 99% of the time, it's always better. Can any of you think as to why it could sometimes be slower to do a double start than a single start for A-star? Okay. So the reason why it could sometimes be slower is that depending on how your wall is constructed, it could be the case that the two algorithms try different paths and overall, because it also depends if they have the same heuristic. It also depends if they have the same heuristic. But what can happen is that if the two heuristics contradict themselves and then they're going to go in different paths, they're going to end up covering more space than they would have if you only had one start. Although, as I said, yeah, that's a very good example of it. See, if you only use one of them, then you only have gone. Normally, if you use both of them, then it does more computations than it actually has to. Yeah. Any other questions? Well, that's about it for our presentation. Thank you for paying attention. I hope it was interesting, or at least thought-provoking.